Logistics is both complicated and complex, and in this presentation I shall explain why, what tools we have at our disposal to deal with that complexity, and in particular how we can use those tools to deliver net zero freight emissions. I want to start by revisiting the original challenge. We first started treating climate change seriously in the UK in about 2010. And the science then told us that we needed to reduce carbon emissions by about 80% to stay below a 2 degree centigrade rise in global temperatures. And in 2010, that transition to an 80% reduction looked achievable. It looked as though we could do it in a smooth, gradual and manageable way. However, since then, CO2 emissions have continued to rise, and they are still rising, and that means that we've used more of the carbon budget than we originally anticipated. The carbon budget is the amount of carbon we can afford to put into the atmosphere and still stay below, in this case, the 2 degree centigrade rise in temperature. And because we've used more of the carbon budget than we anticipated, the reductions that we need to achieve now have to be much faster and much more. So remember, this graph is actually related to a 2 degree centigrade rise in temperature, and we are now tied into a 1.5 degrees centigrade rise in temperature, and we're no longer talking about an 80% reduction, we're actually talking about net zero. So this graph actually underestimates the size of the challenge. So what does the science tell us now? Well, this is the most recent graph I've seen from the IPCC, and the curves that you can see here represent the change and the probability of that change delivering 1.5 degrees C. So the most gradual change that you can see on this graph has a 17% chance of preventing a rise in temperature greater than 1.5. The steepest graph has an 83% chance of keeping us below 1.5 degrees. And if you take that 83% graph, the curve on the left here, then it's sort of indicating that we need to achieve about an 80% reduction by 2030 to 2035. And that's a significant challenge. This compression of time has an impact on the logistics system. And to illustrate that, I've decomposed the logistics system into a set of subsystems. So we have the operations system, which is the day-to-day operation of logistics, the operational planning system, which takes a slightly longer term view of things in terms of planning over a week, say, or even over a month, the strategic plan, which takes a sort of 2, 3, 5 year view of what the strategy for operations should be, the technology system, which is the trucks, vehicles, technology that we deploy in our warehouses, which has a longer time horizon, and the energy system, which we haven't seen change for many years until fairly recently. And the horizons of each of these systems determines their clock speed. So the operations system is operating quite quickly, that has a fast clock speed. The energy system operates in a slower sense in the context of logistics at least, and so that has a slower clock speed. And the compression of time produced by the need to reduce our carbon emissions quickly and dramatically compresses all of these systems so that they become much more aligned. And when they become more aligned, then bearing in mind that each of these systems has changes going on all the time, we increase the chance of probability of coincident events resulting in dramatic changes, because when we get a coincident event, then an event in one system gets amplified by the events in other systems, and you can also get these sort of cascading effects through the system of systems. So a big change in the strategic plan causes big changes in the operational plan and the technology system, and these then feed through the system and are quite difficult to predict and even more difficult to manage. So we have a way of thinking about this in terms of how we conceptualize these complex systems. And we tend to think of them as what we call rugged landscapes. This is a graph, and the vertical axis I've called performance, and that's quite broad, but it could mean anything. And performance is plotted against 2 dimensions, or 2 parameters, or even 2 sets of parameters. And what we can see is that there are lots of different areas in the graph where we have different levels of performance, and there's some areas where we have very poor performance. And this is what we call a rugged landscape. Now, the object of the exercise is to find the highest peak, the highest level of performance, and then change the parameters of the system to allow us to sit on top of that highest peak. Now, in this particular instance, it's worth noting that the peak is very narrow, and small changes in the parameter space may mean that we fall off this peak quite easily. Okay, so this is quite a fragile position for us to try and maintain. Nonetheless, if we're trying to seek the best performance in this rugged landscape, then we need to find a way of changing the parameters so that we sit on top of that peak. Relatively easy to do if we can see the whole landscape, which of course in the real world is actually very difficult to achieve. It's very difficult to know that if you change the parameters that you know locally, what the impact would be, and whether that takes you to the highest peak or some other place. And that's not the end of the story. So these systems are dynamic, which means that they are constantly changing. The parameter space and the consequences of the parameter space means that the changes result in peaks growing, disappearing, moving to different parts of the landscape. And so not only do we have the difficulty of finding the biggest peak at one instant in time, we have the challenge of predicting whether that peak is going to exist in a few months, years, decades time. So this is a complicated challenge. If we take that landscape, both from its sort of initial state and through its transition to this landscape, then we would, in an ideal world, we would have avoided climbing the highest peak, which promptly collapsed and left us in a sort of a pool of despair in a area of relatively low performance, and we would have chosen to climb this peak, which wasn't as high but did persist through time. And we called these peaks robust and fundamental structures. They are always there. So there are always some parts of this highly dynamic moving landscape that exist in time and stay, and providing that they have superior performance to the state that we start in, these are attractive places to navigate to. Now that's all well and good conceptually, but we can't see into the future, not in the real world. We don't have a means of time travel, and particularly when the future is quite uncertain, it's very difficult to base an assessment of the future on the past. So what should we do to navigate these complex landscapes? How do we make sure that we find a peak that is going to last in time and give us a satisfactory level of performance? Well, there's good news. So we have, in the last decade or so, increased the amount of computing power that we can access. And that means that we can run increasingly sophisticated computer models. And one way to create these complex landscapes and understand them better is to use a class of models that we call agent-based models. These agent-based models are virtual worlds, but they are high-fidelity virtual worlds, and we can initialize them using the current state of whatever it is we're trying to model. We can then run them at a very fast clock speed, which means that we can glimpse the future. So we can see how a system initialized on today's conditions will change. But given the level of uncertainty that we have to accept into these models, we have to run them for thousands of different parameter settings so that we can understand the sensitivity of the virtual world to small changes. We can understand how that landscape will change, and through that we can have a much better go at identifying robust fundamental structures. The peaks that aren't the best peaks to climb, but they are always there. The things that offer us overall system improvement. So we have three models here, just to give you an indication of the type of thing that we can do. The model on the left was a model that we've built recently to explore how we can best distribute COVID vaccines in any country. And what we found is that there is a better way of doing this. We can incorporate into that model residual values and how we may use cold chain assets, not just in vaccination, but how we may transfer them into other supply chains, and that changes the business model and so on. The model in the middle, which is borrowed from Dr. Krista Searle, who's joined us from South Africa, is looking at how you incentivize people to relocate bikes in a bike scheme, electric bike scheme, so that they are more favorably positioned for future needs. And the model on the right is looking at parcel deliveries and how you position transfer points from vans to e-bikes and from e-bikes to people delivering parcels as pedestrians. So all these models have one thing in common, and that is that they are all system of systems, just like the logistics systems, and those systems interact with each other. So the effect in one system will spill over into an adjacent system and vice versa. So they do reflect the complexity of the real world. They are, of course, an abstraction, and we can't take their output as gospel. So we also need to match this modelling approach with a way of acting in the real world that enables us to respond to the complexity and the possibility of coincident events occurring in different systems. So at this point, I want to introduce you to 40-second Boyd. Now, 40-second Boyd, for those of you who haven't come across him before, was a general in the United States Air Force during the Korean War. And he was a pretty good pilot. He had a standing bet that he could turn a position of disadvantage to a position of advantage in less than 40 seconds. And we're talking about dogfights here. And he never lost the bet. He always managed to win. And the way that he did that became of interest to the Pentagon. So they took him out of combat and they moved him into what I shall call Top Gun school. And they said, can you teach all our pilots to be as good as you? Can we clone 40-second Boyd? And the system he came up with is still taught to Air Force pilots across the world, is called the OODA loop. And OODA stands for Observe, Orientate, Decide and Act. Now the reason I'm introducing this is that the OODA loop is now also taught in business schools as a way of dealing with complexity and uncertainty. And it's worth spending a few moments thinking about how this could be used to achieve net zero. So the thing about the OODA loop is you have to execute it fast in a dogfight. That's really how you win. So the questions that we can pose to businesses and possibly regulators is how do we execute the OODA loop faster? Now the observe bit for us is really about data collection. How can we collect data so that we can throw them into our computer models so that we can run them and having run them once, recalibrate them with the next set of observed data. This is the observe feeding into the orientate. So observe, collect data, orientate, run computer models. And we have to do it in computer models because we have no way of creating the type of real world experiments that we would need if we were to do this in a more traditional way. One, because of the scale of those experiments, and two, because of the length of time that it would take to run them, and events could possibly outpace us. So we have to run computer models, and those computer models should inform the way that we make decisions, and then we have to find ways of promoting the right decisions with rewards and discouraging inappropriate decisions. So where are we in this OODA loop? Well, we started research into how you can decarbonise road freight about 10 years ago, and 10 years ago was the first time I mentioned to authorities that we didn't have enough data, and that if they really wanted to be serious about reducing carbon emissions, then we need to find a way, first and foremost, to collect logistics data. The logistics data exists. I mean, nothing in logistics happens by accident. It's all planned. So the data exists. We need to capture it. We need to build our capacity to run and experiment with computer models so that we can make better decisions, and then we need to act in appropriate ways, both as regulators and as businesses, and arguably as individuals. So, in summary, the logistics system is a complex system. And because it's complex, there is now an increased probability of an extinction event. And that is because we've compressed time and we've synchronized clock speeds of the different systems. The good news is we have tools and approaches appropriate to navigating changes in complex systems. And we need to find ways of making the most of these tools. And to do that, we need to collect more data. That data needs to be standardized so that all flavors of tools can use it. And we may have to find new ways of sensing that data in the real world. But if we can do all of that, then we can solve the problem. And we can solve the problem by using novel ways of analyzing the situation. And to quote Einstein, we should remember we can't solve problems by using the same kind of thinking we used them when we created them. Thank you.